Hey folks, I'm Dia, and this is the next chapter of the Pseudo-Focus series. In the following weeks, we will uncover new ground without uncovering new ground. We will learn something new without learning something new. And we will smoothen our brain without smoothing our brain. We have experienced algebraic troubles and visual wonders along the way when finding the pseudo-foci of functions. And speaking of functions, we all know that their behavior always goes from left to right, and never turns back to go right to left. This is a common trait shared among functions, that they can't have an x value with two y values. However, this means we still have a limited possibility of curves to find the PF of, because ask yourself, how can I find the pseudo-focus of some curve if it can have an x value with two y values? And how will normal lines, normal maps, and cone graphs behave or function upon finding the PF of a more general curve? Well, there are a variety of ways to draw and express a more general curve than a function, and one of those ways is expressing a curve through a parameter. Before I define to you what parameters are, let me first tell you that you've actually seen parameters as early as episode 4. You know those two cusps, quote-unquote, looking at x cubed? Those are parameters. Those cusps are a graph of a parameter because, for one, they have x values that intersect two y values, and through the mighty vertical line test, we can prove that it's not a function. Parameters, man, we made them up. But what are they, really? In my intuition, a parameter is a hybrid between a coordinate and function. But what makes a parameter is that instead of y depending on x, y and x depend on another variable t, where that variable mainly determines the points on the curve. One example of a parameter is t squared, which is a parabola. When we set different values of t here, we will get a table of values similar to f of x equals x squared, because in a way, we can also express the function as f of t equals t squared, because x equals t. Same happens for example, t to the power of t, which is just f of x equals x to the power of x, because the x coord is just t, making x equals t. So the function can also be f of t equals t to the power of t. However, this is not new ground for us to cover. No pun intended. What we're here for are the two y value making, not a function thingies. So what if we do, for example, t minus t squared, t plus t squared? Glance at this curve for a sec. This is interesting, since the abscissa, or the x value, is not equal to t, but equal to the parabolic t minus t squared 1, its x behavior goes left to right, then turns back, right to left, like a sleeping parabola. Let's look at the table of values. If t equals 0, we get 0, 0. If t equals 1, we get 0, 2. If t equals 2, we get negative 2, 6. And if t equals negative 1, we get negative 2, 0. And hey, negative 2, 6 and negative 2, 0 ride on the same x value of negative 2, proving the parameter cannot be a function from its entire domain. To add to the parameter's uniqueness, watch as I slide the value of t from negative 5 to 5. It is these kinds of functions, curves rather, that we will find the pseudo-focus and normal maps of. And let me tell you, it's gonna be a wild ride. Expect that in the next episode. See ya.